Hello everyone, this is Abhinav and today we'll be discussing the ninth problem from the CP-31 sheet by TLE Eliminators under the 1500 rated problems. So let's move on to our CP-31 sheet and we can see that the 1500 rating mark has been checked and we'll move on to the ninth problem, which is factorials and powers of 2. Okay, let's read the problem statement. It states that a number is called powerful if it is a power of 2 or a factorial. Okay, in other words, a number m is powerful if there exists a non-negative integer d such that m is either 2 to the power d or m is d factorial. Okay, and so you know what d factorial is. It's the product from 1 to d. For example, 1, 4, 6, these are powerful numbers because 1 is a factorial of 1, 4 is 2 to the power 2, 6 is 3 factorial, but 7, 10, 18, they cannot be represented either as a power of 2 or factorial, so they are not powerful numbers. Okay, so you are given a positive integer n. Find the minimum number k such that n can be represented as the sum of k distinct powerful numbers, or say that there is no such k. So we just need to find, we are given the definition of powerful number. So either if it is a power of 2 or a factorial, then it is a powerful number. Now we need to form a positive integer n using k distinct powerful numbers such that we minimize the value of k. Okay, so we need to find the minimum number of distinct powerful numbers which can form n, the sum of which would be n. Okay, so n is given up till 10 to the power 12. That's the main thing. Okay, so basically what we need to find is, we are given some n. Okay, let's say n is 15. Okay, so what we need to do is we need to make this 15 using least number of powerful numbers. What are powerful numbers? Powerful numbers are all the powers of 2, like 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, okay, and so on, 2 to the power any x. All these are powerful numbers. Along with that, all the factorials, like 1 factorial, which is 1, or we'll start with 0 factorial, which is 1. 1 factorial is also 1, and then 2 factorial is 2, 3 factorial is 6, 4 factorial is 24, 5 factorial is 120, and so on. So these numbers and these numbers, all these numbers combined are powerful numbers. So using these numbers, we need to use minimum distinct numbers among these to form 15. So for 15, what we can do, one possible way is, maybe we can use a 6, let's suppose, then 9 is remaining, and along with that we can use an 8 and a 1. Okay, so if one possible way is use a 1, use a 8, 9 plus 6, 15. Okay, so 15 can be formed using 1 plus 6 plus 8. So in this way we are using 3 distinct numbers. Okay, is there some way through which we can do it in even lesser? Can we do it in just 2 distinct numbers? Okay, so if you want to do it in 2 distinct numbers, I think among these numbers it's not possible. After 8 we'll get 16. Okay, so we cannot use anything greater than 15 to make 15. So if we use 8, we don't have a 7 here. If we use 4, we don't have a 11 here. So we cannot do it in just 2 numbers. So 3 is the minimum for this test case. Okay, so I hope you understood what the problem wants you to do. Now, how do you do that? If we analyze the constraints of the problem, n is given up till 10 to the power 12. Okay, so n is up till 10 to the power 12. What does that mean? We cannot do something of order of n. Okay, if we write a program of something of order of n, then 10 to the power 12, this won't be accepted. So we need to do something better than order of n. So which can be something like order of log n, or maybe some other time complexity which would not exceed 10 to the power 8. That's what we need. Or we also have 100 test cases. Okay, so for each test case we have to do, so for each test case we need to do in 1e6 at max. So maybe we can do it in square root of n. Okay, that would be barely accepted, or anything lesser than that. These are our, we can say, are our expected time complexity. So we'll look at how we can do it in this time complexity. First, let's analyze the problem, what we need to do. Okay, so we have two types of powerful numbers. One is the powers of 2. Okay, all the powers of 2. Okay, these are the two types. This I am telling as type 1, and this I am telling as type 2. Okay, now just imagine for once this type 2 doesn't exist, let's say. Okay, we only have these numbers which are called powerful numbers. Let's assume for once. Then what would your answer be? Whatever number you are given, what would you have to do? If you are only allowed to use powers of 2, then using distinct powers of 2, you need to form a number n with minimum number of distinct numbers. What is that? If you just observe a little bit, if you think a little bit, what is that? That is actually the binary representation of that number that represents the same thing that we need to find. Like 15, the binary representation of 15 is 1111, which is, this one is for 2 to the power 0, this is for 2 to the power 1, 2 and 3. So basically this 15 is 2 to the power 0 plus 2 to the power 1 plus 2 to the power 2 plus 2 to the power 3. Is it? So 2 to the power 3 is 8, 2 to the power 2 is 4, 2 to the power 1 is 2, 0 is 1. So this is what 15 is. Just take any other number. Let's say we are taking n is equal to 10. Binary representation of 10 is 1010. So this is at 0, 1, 2, 3 position. So this represents 0 means we are not taking this power, 1 means it is 2 to the power 1, and this 1 means 2 to the power 3. So this 10 is actually 2 to the power 3 plus 2 to the power 1, which is 8 plus 2 is making 10. So whatever number you take, the binary representation is what? It's how you can represent the number in powers of 2. That's what the binary representation is. So if I would only have these numbers as powerful numbers, then my answer would be the number of set bits in the binary representation of that number. That's what our answer is going to be. For 10, there are 2 set bits. That means we can represent this number using 2 unique numbers, which are powers of 2. For 15, we have 1, 2, 3, 4. 4 bits are set in this number. So we would need 4 numbers to represent it as sum of powers of 2. Okay, so this thing is clear. Now, with this problem, what we also have these numbers along with that, which are factorials of some numbers. Okay, so first of all, let's see how many possibilities of these numbers exist with us. Okay, so till 5 factorial I had written. Let's say I'm writing more. I'm writing 6 factorial. That would go like 720. Yeah, 7 factorial, 720 into 7. That would again go some very big number. And you'll realize your n is up till 10 to the power 12. So if let's say my some k factorial goes more than 10 to the power 12, that means I would never use this k factorial, because if I'm using any number greater than 10 to the power 12, I would never use that number to form something less than 10 to the power 12. So which factorial goes par 10 to the power 12? Like if you just observe a little bit, then 15 factorial is approx 1.3 into 10 to the power 12. Okay, so this is approximately this, which is greater than 10 to the power 12 obviously. Okay, so if you are using 15 factorial, your range would exceed. That means the only possible numbers that we can use in this type 2 are from 0 factorial to 14 factorial. Okay, so 0 factorial to 14 factorial, these are the only numbers that we can use from the type 2 category. Okay, so these are total just 15 numbers. And among that also, if you look, this 0 factorial is 1, 1 factorial is 1, 2 factorial is 2. These three numbers already occur in our type 1. So they are already powerful using the type 1. So you may assume that they don't exist in type 2, because if any number can be represented as power of 2 or a factorial, assuming that as any one of them would make it powerful. Okay, so we don't need to consider them two times. Okay, we need to consider them one time only. So what I'm doing is I'm removing these numbers from my type 2 category. Okay, so in my type 2 category I'm starting with 3 factorial. Okay, so that I have unique numbers, because if I'm using some number from type 2 which also exists in type 1, then I may use it two times. So I'm just removing them from my type 2 category. And if you look from 3 factorial up till the 14 factorial, none of the numbers would come in type 1. Why? Because in type 1 we have numbers which are purely powers of 2. No other prime factor exists. But in them, in 3 factorial, you would have a 3. It's 3 into 2. So this won't exist. In 4 factorial, again you would have a 3. Okay, so in all the factorials above that, you would have something other than 2. So they would never form a power of 2. Okay, so now these two are distinct. Like you can say, all the numbers that exist in this, they don't exist in this, and all the numbers that exist in this, they don't exist in this. First of all, after removing them, that's what we got. Now how many numbers we have in the type 2 category? So 0, 1, 2 factorial are removed, so 3 to 14 factorial, which are a total of 12 numbers. Okay, so these 12 numbers that we have, these, if we can somehow analyze which numbers among these 12 we need to use, then after using them for the remaining sum, the minimum numbers required among them, that can be directly computed, as I told, using the number of set bits. Okay, so this thing I had already concluded, that number of distinct type 1 numbers to form x is equal to the number of set bits in x. Okay, this conclusion we had already made. So once you know this conclusion, then what is remaining with us is what all type 2 numbers do we use. Okay, so what we can do, we only have 12 such numbers. We only have 12 such numbers. So we can just check all the possibilities of using those 12 numbers. What are all the possibilities of using a set of numbers among some n numbers? Okay, every number either we would pick up and use, or we would not use. Okay, so 3 factorial, either we would use or not use. 4 factorial, either we would use or not use. Okay, the numbers that we would use, the sum of them would form the sum that is formed from type 2. So how many possibilities exist for 12 such numbers? It's 2 to the power 12 possibilities. Okay, so there would be 2 to the power 12 possibilities using these 12 numbers, 2 to the power 12 possibilities of the sums that we can form using these 12 numbers. So this 2 to the power 12 is not very large. It would be like approx 10 to the power 3, or 4 into 10 to the power 3, approx this. So we can just run through all of these. Okay, all of these possibilities, and for any one particular possibilities, let's say in one particular possibilities we are taking 3 factorial, and let's say in one of the possibilities we are taking 3 factorial and 6 factorial and 7 factorial, let's say. Okay, so this would form some x, and if we needed to form a sum of n, then we have used 3 numbers here. How many more numbers we need to use would be n minus x is the remaining sum, and this sum would be formed using the type 1 number. So number of set bits in this. So we would say our answer would for this would be 3 plus number of set bits in n minus x. Okay, so using 3 numbers, if we are forming a sum of x, 3 numbers of type 2, then the total numbers required would be 3 of type 2 plus set bits in n minus x would give the number of numbers required in type 1. So these would be the total numbers. So we can just iterate through all such possibilities, all of these 2 to the power 12 possibilities, and inside that, for calculating the set bits, the number of bits sets in a number, its time complexity for 10 to the power 12, there would be like approx 40 bits, the first 40 bits that can be set. So you can say like log n would be the time complexity in which we can just go through all the bits and check if they are set or not. Okay, so a number n has total log n bits. Okay, so our overall time complexity would be 2 to the power 12 multiplied by log n. So in this time complexity, we can just search through everything. This would be approx 2 to the power 12 is 4 into 10 to the power 3, and log n is for n as 10 to the power 12, log n would be approx 40. Okay, we may even check up till 60, there is no problem. Okay, so this thing would be like 1.6 into 10 to the power 5. So this multiplied by the number of test cases, there are 100 test cases. So 1.6 into 10 to the power 7, this would be well accepted. Okay, so I hope you understood the complexity and the logic, basically what we need to do. So we just needed to divide these numbers into two types, and for the first type we needed to observe that if we want to form a number using powers of 2, the binary representation is that only. The number of set bits in the binary representation would be our answer. Now in the type 2 numbers, the total numbers that exist in type 2 are very less. It's only 12 distinct numbers that exist there. So we can just iterate through all these 2 to the power 12 possibilities, and for them just after that calculate the set bits in the remaining numbers to get our overall answer and minimize among all the possibilities. So this was the overall logic. I hope you got it. If you just dry run in maybe one of the test case, let's take n is equal to 11. So for n equal to 11, what all numbers we can use in, first of all we'll use the type 2. So 3 factorial is 3, 4 factorial is 3 factorial is 6, 4 factorial is 24, 5 factorial is 120. So for 11 we would never use more than 3 factorial. So we only have two possibilities, either we'll use this 6 or not use this 6. Okay, so first if you use this 6, okay, then the remaining number would be, okay, so if 6 is used, then the remaining number would be 5. So the total count will be 1, that is 6 plus number of set bits, in 5. Okay, so how many set bits are there in 5? 5 is actually 101. So there are 2 set bits. So 1 plus 2 is 3. Okay, other possibility is 6 is not used. Okay, in that case what do we have? If 0, so no numbers are used among type 2, and number of set bits in 11. So binary representation of 11 is 1011. So number of set bits is 3. Okay, so in both the cases we got 3, so minimum among them would be 3. So our final answer would be 3. For the second test case, we can see our answer is 3. Okay, I hope the dry run is also clear and the complete logic is clear to you. Let's move on to the code, what we need to do here. Okay, so first of all, in order to calculate the number of set bits in an integer, I've created this function. I'm just returning built-in pop count lln. So in C++ we have this built-in pop count function which would return the number of set bits in a integer n. Okay, if you didn't knew about this function, you could just iterate through all the bits from 0 to 60 and check if it is set, then add a +1 to your answer. You can do that as well, or write a recursive function. There are multiple ways to check the number of set bits. Okay, so this is a direct function which is already present in C++, so I have used it. Okay, now I'll move on to my solve function, what I'm doing. Okay, so this is my main function where I'm taking the t test cases as input, and for every test case I'm calling the solve function. Okay, so inside the solve function, I've written my real logic. Also, I have defined my int as long. So you can see that the range of n was up till 10 to the power 12. So this exceeds the int range. So if I'm using int, then my range would exceed. So I need to use long here. So I have defined my int as long. So all the int that I have written here in my code are actually long. Okay, so you can do that, and only thing you need to consider in that is you need to write int32 in your main function. Otherwise, if you're writing int, that would get converted to long and give you an error. So here you need to just make sure that after that all your int would be converted to long. Now what I'm doing inside my solve function, I'm taking the input n. After that I have to compute the factorials up till 14. Okay, so all these possibilities, these 12 numbers from, as I had written, these 12 numbers from 3 factorial up till 14 factorial. So I need to first compute those numbers. So factorial of 0 is 1, and from I equal to 1 to 14, factorial I is factorial I minus 1 into I. So this way I just computed all the factorials up till 14. After that, in my in a vector vec, I'm just storing all the numbers in type 2. So from 3 to 14, so factorial 3 to factorial 14, these are the 12 distinct numbers that would exist in my type 2 category. So I have pushed those numbers in my vector vec. Okay, now I'll iterate through all the possibilities of those 12 numbers as being taken or not taken. So one way is you can do it recursively, take and not take that way, or you can use a bit mask to do that. So I'm running a loop for mask equal to 0 up till mask less than 2 to the power 12. So this way this mask is going to iterate through all the possibilities of from 0 from the 12 numbers of being either taken or not taken. Okay, so in this mask, if the ith bit is set, okay, so I'll check if the ith bit in this mask is set, that means this ith number is taken. So I'll add to the sum vec I and also increase my count, that how many bits are set already taken, how many bits are already taken from the type 2 category. Okay, so for any mask, I'll just check if ith bit is set, then I'll add to my sum and increase my count. Okay, so after this, I know I have got a sum using those type 2 numbers, using a set of those type 2 numbers. If that sum already exceeds n, that means we cannot form n using that. We have already exceeded that. So I'll put a continue. I'll just ignore that case. And if not, then in my count variable, I'll add the number of set bits of n minus sum. Okay. So as I had shown, my answer would be how many we have already used plus the number of set bits in n minus x. So x is the sum here. So number of set bits in n minus sum will add. So this count represents one of the ways of forming a number x using count distinct variables. So we'll minimize our answer with this count variable for all the possibilities, okay, of all the 2 to the power 12 possibilities. So this way in our answer we'll get the minimum possible. I had initialized my answer with some very big value, infinity, which is actually 10 to the power 18, so that finally I get my minimum answer. I'll print that. Okay, I hope this code is also completely clear to you. If you look at the time complexity through the code, then what we'll realize, this is just factorial computation, which is taking order of 14 time, just computing the factorials up till 14. This is again an order of 12. This loop is running just 12 times. Okay, now this mask, this is the main function which is taking the time. So this is running 2 to the power 12 times. Okay, the outer for loop, and inside this loop is running 12 times. Okay, just checking for all the bits. Okay. So this is order of 12 here, and this set bits function is going to take an order of log n time. Okay, so and this overall is running 2 to the power 12. So overall this would be 2 to the power 12 into this log n would obviously exceed 12. Okay, log n would be something like 40 here. So I'm writing log n only as the bigger factor here. So overall complexity would be this only, 2 to the power 12 into log n per test case. So overall time complexity I can write as log n into 2 to the power 12 per test case, or I can multiply it with t for the number of test cases. Okay. This is basically log n, I can say, is approx 40 for the given n. 2 to the power 12 is approx 43, and number of test cases is about 100. So this is like 1.637. So this would be well accepted. For the space complexity, what is our space complexity? Our space complexity is, we are using this vector of size 15, this vector of size 12. Okay, and these are just normal variables. So space complexity is order of 14, you can say, just. Okay, so I hope this problem is completely clear to you. The main thing to observe here was how you can observe a number as sum of powers of 2, which is actually the binary representation of that number. And then if you are taking the factorials increase in a very speedy manner. So 10 to the power 2, for 10 to the power 12, only 14 factorial would exceed that. So there would be very less numbers of type 2 of factorials. So these were the main observations from this problem through which you can solve this problem. I hope it is completely clear to you. Thank you so much for tuning in.